Now we turn to cost. We know a good structure is fast, but how do we measure fast and slow in a fair way? Let us build a simple cost model that works for every structure in this course. We measure cost by growth. That means we watch how the work grows as the input gets bigger. The input size is called N. To do this fairly, we follow 3 simple habits. First habit, we ignore constants. A step that is twice as fast is still the same kind of growth. We care about the pattern, not the exact number. Second habit, we ignore small input noise. When N is tiny, everything is fast, so tiny inputs do not tell us much. We care about large N. Third habit, we compare the shape of growth. Does the work grow slowly or does it explode? The shape is what really separates a good structure from a bad one. There are 2 things we can measure. The first is time. Time means the number of basic steps the operation takes. The second is space. Space means the extra memory we use, beyond the input itself. We also pick which case we are talking about. The best case is the luckiest input, where the work is smallest. The average case is a typical input, the kind you usually meet in practice. The worst case is the hardest input. This is the guarantee we usually quote, because it tells us the operation will never be slower than this. So keep these points close. Big O describes the shape of growth, not seconds on a clock. 3n plus 100 and half of n are both big O of n because they grow the same way. Unless we say otherwise, we quote the worst case and we use the simplest usual class. These are the growth classes you will use every day. Start with big O of n. Think of washing dishes. 1 more plate means 1 more wash. So if you double the plates, you roughly double the work. The cost grows in step with the pile. Now big O of n squared. Think of a party where each guest shakes hands with everyone already there. Every new person greets the whole crowd before them. So if you double the guests, the number of handshakes grows about 4 times. This cost explodes much faster. Now look at the full order from cheapest to most expensive. Big O of 1, then big O of log n, then big O of n, then big O of n log n, then big O of n squared. You will see this latter in every later cost table. One warning, big O of 1 does not mean 1 line of code. It means the cost does not depend on n at all. A single print line looks short, but if it sits inside a loop over n items, it runs n times. So it is big. O of n always counts steps, not lines. Let us draw these classes on one picture. We fix one machine and we grow n to the right. This flat green line at the bottom is big O of 1. The cost never changes, no matter how large n gets. Just above it is big O of log, and it is almost flat too. It rises, but very slowly. Even for huge M, it stays low. This indigo line is big O of n. It is a straight, steady climb. Double the input and the cost roughly doubles. The amber curve is big O of n log n. It bends upward faster than the straight line. This is the cost of good sorting. And this steep red curve is big O of n squared. It shoots up very fast and soon runs off the top of the chart. This is the real lesson of the picture. At small n, every curve looks cheap, but as n grows, they pull apart sharply. That gap is the whole reason we care about the growth class. Let us put real numbers on those curves. We fix 1 step per microsecond. Now predict first. The input size is 1 million. The shape is a loop inside a loop. Do you think that costs a few million steps or something much worse? Start small with n equal to 10. Big O of 1 is 1 step. Big O of log n is 3. Big O of n is 10. Big O of n log n is 33. And big O of n squared is 100. At this size, they all look close. Now n is 1000. Big O of 1 is still 1 step. Big O of log n is only 10. Big O of n is 1000, but big O of n squared has jumped to 1 million. The gap is opening fast. Now n is 1 million. Big O of 1 is still one step. Big O of log n is just 20. Big O of n is 1 million, and big O of n squared is 1 trillion. That is a huge number. Let us feel that last number. At 1 million items, big O of n squared is about 1 trillion steps, which takes about 11 days. But big O of log n is only 20 steps, about 20 microseconds. This is why a demo that worked on 100 items can die in production on a million. One warning though, constants can win when n is small. A big O of n squared routine may beat a big O of n log n1 when n is only 8. So profile when your inputs are small and fixed. Let's meet one more idea before we meet it. Some operations are not steady. Most of the time they are cheap, but once in a while one call is expensive. So we do not judge these operations one call at a time. We judge them across a whole run of calls. We take the average cost per call. That average is called amortized analysis. A good example is adding to a dynamic array, which you meet in Chapter 3. Almost every add is cheap, big O of 1, but once in a while the array is full. Then it must grow and copy everything, which costs big O of n. The trick is to double the size each time the array grows. When you spread that one rare big cost across all the cheap adds, each add costs big O of 1 on average. We call this amortized big O of 1. Hash tables in Chapter 13 use the same trick. For now, just learn the word. This table is our cost dictionary. Every one of the 21 chapters uses these same 4 terms. Let's read them one at a time. Big O of f means an upper bound. It is the worst case we promise, unless we say otherwise. This is the ranking we use to compare structures, from cheapest to most costly. 1, then log n, then n log n, then n squared. Space means extra memory, beyond the input itself. Amortized means the average cost per operation, taken across a whole sequence of calls. Dynamic arrays and hash tables use it. Now a quick check. Label each one as big O of 1 or big O of n reading R at index 7, finding the largest value in an unsorted array, returning a stored size counter, printing every element of a list. Try it before the answer. Now the answers. Reading one slot is big O of 1. Finding the largest value is big O of n, returning a stored size is big O of 1. Printing every element is big O of n, remember. Big O of 1 means the cost does not depend on, and it does not mean the code is one line.